Hello geometry students, my name is Jami Emigh, and this video is our discussion on section 11.3, surface area of pyramids and cones. All right, what is a pyramid? A pyramid is a polyhedron, so remember that it's a three-dimensional solid in which one face is the base this time, okay, just one face, which we call the base, can be any polygon, and the other faces, we're going to call the lateral faces, are triangles. So I want to draw the corresponding prism. If we had made this with two congruent parallel bases and connected all these parts, or the vertices, so this one right here, this would be called a hexagonal prism. See how the lateral faces are rectangles? And then this one right here would be a hexagonal pyramid. One base versus two. Sides are rectangles versus sides are triangles. And then those triangles that meet at a common vertex. That's how you get like the point of a pyramid. Think of like the Long Beach State Pyramid. It goes up to one point. It's got one base, triangle sides, and they meet at one common vertex. We name a pyramid by the shape of its base. Okay, so this is a hexagon, so it'd be a hexagonal pyramid. You could also have the octagonal pyramid, triangular, rectangular pyramid. The altitude of a pyramid is the perpendicular segment from the vertex to the plane of the base. So you can see the altitude here. The length of it is the height. And we have base edges, capital B for base, that's going to be the area of the base just like before. Lateral faces, so if you're finding lateral area, it would just be the area of all those triangles added together, whereas surface area would be the lateral area plus the area of the base. All right, let's move on. A regular pyramid is a pyramid whose base is a regular polygon. So this right here would be, it would be a square in that case. For it to be a regular rectangle, that would be a square. And whose lateral faces are congruent isosceles triangles. That's what it takes for this particular pyramid to be considered a regular pyramid. Okay, the slant height. This is one we haven't talked about yet. And it is easily confused with the regular height or the length of the altitude. So be careful. The slant height would be, I like to start by saying, picture yourself standing up here. You're like at the county fair or something. It's that super slide. And the height of the slide, right, would, is that part. But if you slide down the edge of the pyramid like that, that's the slant height. And our formulas are going to be dependent on the slant height. We're using lowercase l for that, as well as the height, which we use lowercase h for that. So make sure to differentiate between those two carefully. The lateral area of a pyramid is the sum of the areas of the lateral faces. So this is a net of that pyramid that you see right there, and it is showing the derivation of the formula lateral area, which is equivalent to the perimeter of the base, capital P, times the slant height, lowercase l, and then you divide that by 2 or multiply it by 1/2, and that's how you get the lateral area of a pyramid. To get the surface area, you just take that lateral area, and just like before, you add the area of the base. And it's only one base in a pyramid, so you don't see the 2 before the bases like we did in a prism, because prisms have 2 bases. So the surface area of a regular pyramid, is 1 capital B plus half the perimeter of the base times the slant height. Okay, make sure you have that written down somewhere, maybe next to where you wrote those other formulas I suggested you write down from the last section. All right, let's practice. What is the surface area of the hexagonal pyramid to the nearest square inch. Okay, we see here that we have a pyramid, common base, common point there. The base is a hexagon, this 6-sided polygon right there. And we have been given a few measurements. We've been given the 9 inches. That is the slant height, lowercase l. We've been given 3 radical 3. That would be the apothem of the hexagon base. And we're given 6 inches. That is the side length of the hexagon base. All right, so 3 measurements have been given to us. Let's set up our formula, turn it into a blank template, fill in all the blanks, and then do our simplifying. All right, here we go. Formula for the surface area of this hexagonal pyramid is capital B plus 1/2 capital P lowercase l. Let's turn this into 1/2 apothem times perimeter. That came from capital B. We worked on this a lot in the last unit, and that was capital B, or the area of any regular polygon, is the apothem times the perimeter divided by 2. And then we'll add that to 1/2 perimeter of the base, which is the same P times lowercase l. All right, so we have 1, 2, fill it in again right there, and then 3. We have 3 variables to fill in. Apothem, oh, got it, that's 1, nice. Capital P for perimeter of the base, that's just 6 times 2, 3, 4, 5, 6 times 6. So we've got perimeter equals 36 linear inches. And then slant height, oh, which we have that as well, it's 9. All right, so this will be nice. We were given 2 of the variables, lowercase l and lowercase h, and the perimeter of the base, we were given enough information that made it rather easy for us to find it. All right, so let's plug in those variables. 3 radical 3 for our apothem, 36 for our perimeter of the base, and 9 for our slant height. All right, now we just need to be careful with our simplifying, follow the order of operations, and be careful with your radical 3. Don't treat it like a regular 3, the integer 3, it's a radical 3. And if we type that in carefully, we were asked to approximate to the nearest square inches. So you can just type it in your calculator left to right, and we should get approximately 2.55.5307.436. And we're going to round that now to approximately 256 square inches. And that is how many square inches it would take to, let's say, wrap this pyramid in wrapping paper, or to wallpaper a structure like this. It's all 2-dimensional. We're just talking the outside of it, the surface area of it, not the volume, which we're going to get into volume soon, but this is all just surface area, so square inches. All right, the Great Pyramid in Egypt is surrounded by a complex of buildings, among which are smaller pyramids. One of those pyramids includes the Pyramid of Menkaure. I'm not sure I'm saying that right. You can look that up if okay, anyways, use the dimensions to find the surface area of this pyramid to the nearest square meter. All right, so this has clearly been scaled down. We have the pyramid here. It has 68.8 meters as its, well, let me ask you guys, do you think this 68.8 is the height of that pyramid, or do you think it is the slant height of that pyramid? if you said height, you got it right. The slant height would be this distance right here, which looks like it is the hypotenuse of this right triangle. So see that right triangle there created by the height, the slant height, and half of the side. The side length is 110, so half that side would be 55. So just zooming in on this blue triangle right there, it looks like this. And we're going to need to do some work with that triangle. So let's go ahead and get started. We are asked to find the surface area of this pyramid, so I highly suggest you write the formula in its general form, which is right there. And then maybe take a moment to remind yourself what capital B represents, what capital P represents, and what lowercase l represents. And then go searching for those three variables. So I turn those three variables into blanks personally. Helps keep my thoughts organized. First blank is the area of the base, capital B. Well, our base this time just happens to be a square. So that would be 110 side length squared. So that's our first blank. Get my calculator. 110 times itself is 12,100. Second blank is capital P, which is the perimeter of the base. And the base again is a square, so that would be 4 of the side lengths, which is 440. So those two blanks weren't too bad. The third blank is the slant height, and we've already discussed how we can look at that triangle. So the triangle here, that is BCA, that, and half the side is 55. So to find our slant height, we can do 68.8. We can use the Pythagorean theorem. The slant height would be 68.8 squared plus 55 squared equals, that's the slant height squared actually. So the slant height would be, I'm going to have to erase my figure there. So go ahead and sketch that triangle if you need it. I'm going to erase it so you can see the formula. Plugging in the 55 and the 68.8 gives us a slant height of the square root of 7,758.44. So that would be our last blank. Okay, so let's take our capital B plus sign. Went ahead and already did the 440 divided by 2, so now we're talking 220 times the slant height. Approximating that to the nearest square meter would be 31,478 square meters. That is a lot of square meters to cover this, the surface area of this pyramid. All right, let's talk about the cone now. A cone is a solid that has one base and a vertex that is not in the same plane as the base. So we're really similar to the pyramid at this point. And the difference between a pyramid and a cone, or what's more specific about a cone, is that the base, it can't be a square base. It's not sometimes a hexagonal base. It's always a circle. And that is what makes that pyramid a cone. The lateral area is half the circumference of the base times the slant height. So that would be our lateral area equals half of the circumference of the base times the slant height. So that would be like this, circumference of the base times the slant height divided by 2, because it says half of that. And the formula for the surface area of a cone is similar to that of a pyramid, except we're going to take that capital B and put it in terms of pi because our base is a circle. All right, let's see those formulas now. The surface area of a cone is one base, capital B. That base is a circle, so the area of that base is pi r squared. So we now have surface area equals pi r squared for our base, plus that lateral area, which we were developing on the last slide. The lateral area was the circumference times the slant height divided by 2. Let's continue with that. Circumference of a circle is 2 pi r times the slant height divided by 2. Cancel out the 2's, and it looks like our lateral area is pi r l, which is why we add the lateral area of pi r l to get the total surface area of our cone. All right, so all of that being said, you guys, I want you to write down 2 formulas. The one you see right here, surface area equals pi r squared plus pi r l, and also lateral area equals pi r l. Okay, so write those down. Notice that they're only dependent on 2 variables. That's lowercase r and lowercase l. So you may also need to write down that lowercase r represents the radius of the base and lowercase l represents the slant height. All right, so let's practice. What is the surface area of this cone in terms of pi? So leave your answer with the pi symbol in it. Okay, it's asking us for surface area, so we identify that formula, writing it in its general form. So surface area of a cone equals pi r squared plus pi r l. Let's plug in r, which is 15, and l, which is 25. That was nice. We were given both of our variables. So now we just have to be careful with our simplifying. 15 squared is 225. 15 times 25 is 375. Now we can apply addition, which gives us 600 pi. Units are square centimeters. So pi, I want to write this differently. It'd be 600 pi centimeters. Ooh. Let's start over. Let's go with 600 pi. I'm just going to write it as centimeters and then the squared. I don't want you to accidentally think that it's pi squared like that. Okay. All right. So answer is 600 pi units square centimeters. That's the surface area of our cone. Okay, in a chemistry lab experiment, we use the conical filter funnel shown at the right. So that what you see right there is a filter, and we're asked how much filler paper do we need to line the funnel. Okay, so this right here, we have to decide if they're asking us to calculate the surface area of this cone or the lateral area of this cone. And by the filler paper, it's asking to line the funnel. So it would just be this part here, the funnel, okay? So it is not including this top circle, which is considered the base. So it's not asking us for the surface area, it's asking us to calculate the lateral area. All right, so let's do that. And they don't say that so clearly. They don't say find the lateral area. They say how much filler paper do we need. So we have to be careful and be able to differentiate between those. Now we can apply our lateral area formula, which is, the half and the 2 cancel out. So our lateral area formula is pi r l. That's the one you guys should have written down in your notes right there, okay? You can go straight to that. Lateral area equals pi r l. R is the radius. Careful, 80 is the diameter. So the radius would be half of that, which is 40. Slant height, we don't have it. We have the regular height of 45. But we can find the slant height by zooming in on this right triangle right here. If we zoom in on it, it's a right triangle that looks like this. Side length, the legs are 40 and 45 millimeters. Use Pythagorean theorem to find the slant height, and then we get approximately 7,565.95 and so on. rounded to the nearest square millimeter, is approximately 7,566 square millimeters. Just going to write it like this, not that it's wrong the other way, of filler paper. And that will conclude our discussion on section 11.3. My name is Jami Emigh. Thank you for joining me, and I will see you next time for our discussion on section 11.4.